Hello students, in the previous video we have seen the derivation to find the expression for the velocity of a sound wave or the pressure wave, which was obtained as C is equal to root of change in pressure divided by change in density. So this is that was one of the important derivation that we have seen. Now we will continue the concept of velocity of sound and try to link with some of the different variables. The first one will be the velocity of sound in terms of bulk modulus. In the first chapter of fluid mechanics, we have seen what bulk modulus is, and bulk modulus can be defined as the change in pressure or the increase in pressure divided by the volumetric strain. We can write capital K bulk modulus as increase in pressure divided by volumetric strain can be written as decrease in volume divided by original volume. So if I take dP as the increase in pressure and minus dV by V is the decrease in volume to the original volume, then I can write K as dP divided by minus of dV divided by V. Here the negative sign is telling us that the volume is decreasing when the pressure is increasing. So that is the obvious case. The volume will decrease when we press the liquid or we increase the pressure. We know that the mass of the fluid is constant from the mass conservation law. So density into volume is going to give us mass. So density into volume is going to be constant. I can write in terms of notation as the rho into V, okay, in the inverted V form, okay, V with inverted A form as V, okay, just a notation. So rho into V is equal to constant. Differentiating the above equation, they are partially differentiating both of them. Both are the variables. So rho into d of V plus V into d of rho will be equal to 0. When I differentiate a constant, I am getting the 0. So rho dV will be equal to minus V d rho. We can rearrange this term properly, and I can write that minus dV by V will be equal to d rho divided by rho. That means, see, I am relating the change in volume to the change in the density. So minus dou V by V can be replaced by d rho divided by rho. So substituting this in the above equation of the bulk modulus, okay, I can get the K equation as K will be equal to dP divided by d rho divided by rho. I can rewrite this as rho into dP divided by rho. Also I can write this equation as K divided by rho is equal to dP divided by d rho. So from the equations 5.15, that is the velocity of the sound equation, we have defined C is equal to root of dP divided by d rho. So dP divided by d rho can be rewritten as K by rho. So C is equal to root of K divided by rho. This final equation, that is 15.6, where C is root of K divided by rho, gives us the relationship of the velocity of sound with respect to bulk modulus of elasticity and density, right? So I am relating bulk modulus, density, and your capital C, that is the velocity of sound, in this way. This equation is applicable for liquid and gases. Very important relationship. Okay. The next important relationship is relating or getting the equation for velocity of sound for isothermal process. We know the basic equation of isothermal process. We have seen it previously in the starting of this chapter, that is P divided by rho is equal to constant. I can write this as P into rho to the power of 1 minus 1 equal to constant. I am just taking this rho above. Differentiating both the above equation with the variables of P and rho, I can write this as P into differential of rho to the power of minus 1 plus rho to the power of minus 1 differential of P is equal to constant. After differentiating, I get it as P minus 1 rho to the power of minus 2 into dP d rho plus rho to the power of minus 1 into dP is equal to 0. So after differentiating, I am getting this. Let me divide the whole equation by rho to the power of minus 1. After dividing it, I am going to get it as minus p. Okay, I am just multiplying this minus with this p. So minus p, rho to the power of minus 2 was divided by rho to the power of minus 1. Okay, so when I take it up with the indices law, so it will be rho to the power of minus 2 plus 1, so minus 1 will remain. So rho to the power of minus 1 into d rho plus this rho to the power of minus 1 is divided by rho to the power of minus 1, so they get cancelled, so dp is equal to 0. I can rearrange this term in terms of dp. So dp can be written as, taking this term to the right hand side, so dp will be equal to p divided by rho into d rho. Okay, so just rearranging this term, I am taking this rho in the downward in the denominator part, so it will be minus p by rho. Taking it on the right hand side, it will be p by rho into d rho. dp by d rho, I can write it as p divided by rho. Okay, and from the equation of the state, okay, we have defined, this was the first equation we have seen in this chapter, so p by rho is equal to rt. I can write it like that. So this is very, very important. Okay, so now I can use this dp by d rho, which is p by rho, which is rt. Okay, in this equation, which is root of dp by d rho, I can substitute this p by rho as dp by d rho. So p by rho I can put, and p by rho I can write as rt. So c is equal to root of p by rho is equal to root of rt. So this will be the equation for the velocity of sound for a isothermal process. Very important. Let us see for the adiabatic process. Velocity of sound for the adiabatic process. The procedure remains same, only the equation part changes out here. So the first, we will start with the adiabatic process equation. So it is p divided by rho to the power of k is equal to constant. I can rewrite it as p into rho to the power of minus k is equal to constant. Differentiating p and rho, so p into differential of rho to the power of minus k plus rho to the power of minus k differential of p, so dp. Differentiating it, p into minus k rho to the power of minus k minus 1 into dp plus rho to the power of minus k into dp is equal to 0. So dividing this equation with rho to the power of minus k, we are getting minus p k rho to the power of minus 1 d rho plus dp is equal to 0. I can write this equation in terms of dp by d rho, which will be p by rho into k. P by rho can be written as is equal to rt from the equation of the state. So finally your dp by d rho will be equal to krt. So using this in the velocity equation, which is c is equal to root of dp by d rho, that will be equal to krt, or also I can write it as p by rho into k. Okay. So this is very important equation for this is the final equation for the velocity of sound undergoing an adiabatic process. When the propagation is for the minor disturbances through air, the process is assumed to be adiabatic. The velocity of pressure waves or the disturbances through air is very high, and hence there is no time for any appreciable heat transfer. Because the velocity is high, okay, we can take it as an adiabatic process where there is no heat transfer or the heat energy dissipations or the movement. Isothermal process is considered for the calculation of velocity of sound or the pressure wave only when it is given in the problem they mention. Otherwise, you take it as an adiabatic process. If no process is mentioned, then you just take it as an adiabatic process. So these two notes are very important when you are solving the questions or numerical problems on adiabatic or on the velocity of sound for the adiabatic or isothermal process. So please remember, if they are not mentioning any process, consider the process to be adiabatic. If they are specifically mentioning you that it is an isothermal process, then please take it as an isothermal process. Thank you for watching this video. We will see the next topic in the next video.